In this video, we will learn about a new optimization algorithm, that is Water Flow Optimizer. This is a nature-inspired optimization algorithm, and this algorithm mimics the natural behavior of water flow in river, streams, and other bodies of water. Here you can see the list of topics that we will cover in this video. First, we will start with what is this algorithm all about, algorithm inspiration, its working, different mathematical models used in this algorithm, and application. So first we will start with algorithm inspiration. So this algorithm is introduced in year 2021, and author taken inspiration for this algorithm from how water flows through different surfaces. For example, in real life you've seen how water constantly search for simplest way to flow in the direction of less potential energy. So this algorithm simulates the hydraulic phenomenon of water particles moving from high land to low land. So in this algorithm we have two evolutionary operators, laminar flow and turbulent flow. This algorithm mimics laminar flow and turbulent flow of water particles that also include turbulent phenomena like adding, which is often observed in rivers. So as this algorithm simulates how water particles move from higher ground to lower ground. So first we will discuss different behavior of water in nature. So as we all know, water is important component of our life, and it is important for all living organisms, and this is also fundamental components of our bodies. In our bodies, approximately 60 to 70% of our whole body is composed of water, and because of its unique molecular structure and interaction with the environment, water display a wide range of behavior and states. So the simple fact is that water exists naturally in all three states of matter. So this algorithm simulates the primary state of water, that is liquid state. This is used as inspiration for the algorithm operation. So algorithm simulates the movement of water particles from high land to low land. That is similarly how water flow naturally, and this flow behavior is best represented by the liquid water, which is capable of flowing smoothly over surfaces and adjusting its shapes to surroundings. So similarly in this algorithm, solution change and evolve as they explore the search space. So in this algorithm, the evolutionary rule is inspired by the behavior of water flow, where the transition between the laminar and turbulent flow depends on the Reynolds number. So this algorithm is modeled on two key water flow, which represent the behavior of water in nature. So here we have laminar flow and turbulent flow. So both flow have unique patterns of fluid motion, and in this algorithm, the evolutionary rule is inspired by the behavior of water flow, where the transition between laminar and turbulent flow depends on the Reynolds number in hydraulics. So this algorithm used this analogy to determine how water particles move during optimization. So next here we have laminar flow and the turbulent flow. So in laminar flow, water particles move in parallel layer without crossing each other and create a smooth, predictable flow of pattern. In turbulent flow, we have irregular fluid particles and disorganized with eddies, and we have turbulence emerging throughout the path. So here you can see flow pattern. In laminar flow we have smooth, orderly and parallel layers. Turbulent flow pattern we have irregular with swirls and eddies. Energy loss in laminar flow is low due to minimal friction, and energy loss in turbulent flow we have higher due to friction or mixing. Next, we have speed and velocity. In laminar flow, it is steady and we have consistent speed. In turbulent flow, we have rapid changes in the speed and direction. Next, you can see in the laminar flow, we have little or we can say no mixing between layer. But in the turbulent flow, there is mixing. We have layers mixing that leads to turbulent. So in this algorithm, laminar flow represents the steady and gradual improvement of solution, and algorithm moves smoothly throughout the search space, refining the solution without major changing, and turbulent flow represent the exploration phase of algorithm. We have unsteady motion that allow the algorithm to explore more search space and avoid local optima by trying new or random path. So laminar flow is used here for the exploitation, and turbulent flow is used for the exploration. So laminar flow focus on defining current best solution, and in the turbulent flow we have random search, diverse solution that allow the algorithm to explore different possible solution. So next you can see we have different steps used in this algorithm. First we will initialize the population randomly for each particle in the search space. So here we have particles. Water particles means water droplets as the solution, and each water droplet is here a potential solution. After that, we will calculate the potential energy, that is the objective function value. Then we will start the main loop. For each iteration, we will decide whether we will apply the laminar flow or turbulent flow, that is selected based on probability threshold. After that, we have laminar flow. After that, we will apply either laminar flow if the probability threshold value is greater than the random value, else we will apply here turbulent flow. And in turbulent flow, we have further jostling, adding, and overlayer mixing. Then we will evaluate and update position, repeat the loop until stopping condition is met. Now, step by step, we will discuss how this algorithm is working. But first, we will focus on the mathematical models. So this algorithm used different mathematical models to simulate laminar and turbulent flow of water particles, which correspond to two key operators. So these model guide how the water particles, that is the solution, move in the search space to find out the optimal solution. So next you can see here we have different steps used in this algorithm. First we will initialize the position for the water particles I, and for each dimension we will initialize the position, and we will randomly generate the initial position for each particle in the search space using this equation. Here we have lower bound, upper bound, random value. So we will suppose we have lower bound -10, upper bound we have 10, random value we will take between 0 and 1. Suppose dimension we have 2, then for each dimension we will generate a value that is the position of that particle. Like here you can see for agent 1, suppose we have the position for this particle in 2 dimension. So we will randomly generate the position for the each particle. That will calculate the potential energy, that is the objective function value of the position of that particle, position for that ith particle. Then we will start the main loop. While the stopping criteria is not satisfied, we will repeat the loop until stopping criteria is met. And for each iteration, we will decide whether we will perform the laminar flow or turbulent flow, and this we will select based on the probability threshold PL. So here first we will compare the random value with the PL, that is laminar probability. So using this we will proceed the algorithm. If this condition is true, means the probability value is greater, then we will proceed with laminar flow. In laminar flow, first we determine the direction using this equation. After that, for each particle, we will update the position in the laminar direction using this equation, as is here, laminar scaling factor. So first we have laminar operator, or we can say the laminar flow model. So in laminar flow, the movement is smooth and predictable. So the mathematical model for the laminar flow in this algorithm involve making small, steady update to the current solution, that is similar to how water flowing in parallel layer. So laminar flow helps to refine the current phase solution with small adjustments. So here you can see we can calculate the regular motion using this equation. So here yit, that is the possible moving position of the particle, xi, that is the ith particle position, s is here random number that is used to represent the water particle moving value, and the value for s is between 0 and 1. After that you can see this vector d, this represents the direction of motion that all particles carry. So we can calculate the direction using this equation. Done. So here we will compare the potential energy for the particles, and accordingly we will adjust the particles. Here you can see h, that is fixed, that best solution found so far, and here k. So for minimization problem you can see the value for the h, we can see this particle h, it is fixed, and on the other hand we have this particle k. Here we can use any other particle as particle k. So for minimization problems we will consider the minimum value as the best, and if you are solving the maximization problem, then consider the maximum value as the best value. So the best solution found so far is selected as the guiding particle h in implementing the laminar operator. Done. So using this, we will calculate the direction. So laminar flow moving the particles in smooth direction toward wetter solution. Else, if this condition is not true, if the random value is greater than the probability value, then we will switch to turbulent flow. And here further we have jostling, adding, and overlay moving that we will perform in turbulent flow. So in turbulent flow, first we will initialize the trial position. After that, we will randomly select a jostling particle. Then we will randomly select any dimension. Then we will check the probability. We will compare PE value. So we will compare this value with a random value. If the condition is true, then we will compute the distance rho, and we will set the theta equal to this and update the position using this equation. Condition is true, then we will perform adding, else we will perform overlay moving. So as we already discussed, in the turbulent flow, the movement is disorganized and unpredictable. That is helping the algorithm to explore new regions of the search space. Turbulent flow introduces randomness, allowing for large jumps and more exploration. The turbulent flow is used here for the randomness to explore new areas and to avoid the local optima. So in turbulent flow, the water movement is irregular. So this algorithm simulates this by oscillating a particle position in a randomly selected dimension. This means that instead of moving the particles in straight path, the particles movement become more unpredictable. Like in the laminar flow, we have particles movement in the straight path, but here instead of moving the particles in the straight path, we have unpredictable movement for the particles. Here you can see this is the new position for the particle I at any dimension t. Then we have xi t, that is the current position of ith particle in the randomly selected dimension j out of n dimension. And here you can see we have mutation value b, that is used to determine how much the particle position will change. And here, change is determined based on two possible transformation, adding transformation and overlay moving transformation. So first we have adding transformation. So here with the probability value PE, this transformation simulates the swinging circular motion of water in an eddy. Next we have overlay transformation with probability 1 minus PE. This simulates the general movement of water particles across different layers. Here you can see the comparison is done if we have two control parameters R, that is a random value between 0 and 1, PE, that is here adding probability value. So we have two control parameters. So we will check if the random value is less than the adding the probability value. If this condition is true, then we will apply here eddy transformation, and this transformation will generate the position based on spiral like movement. Otherwise we have here overlay moving transformation that will simulate the movement of particles in different dimensions. So next you can see here the mathematical model for the adding transformation. So this transformation simulates the behavior of water particles moving in circular patterns, like we have addings in rivers or in turbulent flow. So this is modeled using this equation. Here theta is the random angle within the range minus pi to pi. This simulates the sibling nature of eddies. Rho is the distance between the particle I and another randomly selected particle k in the same dimension j1. So this acts as the shearing force between particles that we will calculate using this. And the resulting position is calculated by adding the oscillating movement to the particle's current position. Here the oscillating movement is controlled by theta and rho. Next we have overlay moving transformation that simulate the behavior of water particles moving from one layer to another. It uses a linear transformation between upper and lower bound. of the search space and the position of another particle k in the different randomly selected dimension j2. Here you can see we have upper bound 1, upper bound 2, lower bound 1, lower bound 2. We have the bounds for the search space in dimension j1 and upper bound, lower bound 2. They are the bounds for the dimension 2. So this transformation ensures that the particles can move across different layers in the search space, that is inheriting the scale of selected particle k in different dimension. So suppose this condition is true. So first we will compute the distance and then we will update the position, else we will select another dimension and update the position for the overlay moving using this equation. Done. And so in this algorithm, first we will select whether we want to perform laminar flow or turbulent flow. If this condition is true, perform laminar flow, else we will perform the turbulent flow. Then turbulent flow we have adding overlay moving. Now suppose we updated the position for the each particle. Now we will perform the comparison. So we will compare the values, older value with the new one, and we will update particles. So here for each particle, if the objective function value of the trial position is better than the current potential energy, we will update, and we will also compare with the global best value. And if the new value is also better than the global best value, then we will also update the global best. So next you can see we have laminar flow that mimicked with the probability PL, which is like the threshold for the Reynolds number. So in laminar flow, water moves smoothly and predictably. So and this phase of algorithm focus on exploitation, that is refining the current solution in a steady manner. On the other hand, we have turbulent flow that occur with the probability 1 minus PL, represent the disorganized and random movements which simulate the exploration in the search space, allowing the algorithm to avoid local optima. So here we have control parameter, that is PL, laminar probability. So PL here, that is the key control parameter of this algorithm that will determine whether the algorithm use laminar flow or turbulent flow. Laminar flow with the probability PL and turbulent flow with the probability 1 minus PL. So this is similar how the Reynolds number control flow type in real hydraulics. Fluid dynamics Reynolds number helps to decide whether the flow is laminar or turbulent. If it is below threshold, then laminar. If it is above threshold, then it is turbulent. So in this algorithm, PL value will decide which flow type, laminar or turbulent, is simulated for a given iteration. And the goal of this algorithm is continuously optimize a given objective function, simulating how water flow from high land to low land, from high potential energy to low potential energy. And at each iteration, if the new position of water particle results in lower potential energy, then it is accepted as the new position. It means either we will perform laminar or turbulent flow, then it will result as a value. Then we will check for the minimization problem. If we have lower objective function value, then we will consider that current position. So we will repeat this loop until the stopping condition is met, and once the stopping criteria is met, we will display the best solution. So here, laminar flow moves the particles in smooth direction toward better solution. Turbulent flow is introducing here the randomness to explore new regions and avoid local optima. Then we have adding and overlay moving. So these two specific methods in turbulent flow used to alter particle position in the search space. After that, the algorithm updates the current and the global batch solution based on new trial position. So this algorithm uses the principles to balance exploration and exploitation as it searches for the optimal solution. Application for this algorithm, we have wide range of application. So due to this algorithm ability to balance between exploration and exploitation, we can use this algorithm to solve complex optimization problem. Here you can see we can apply this algorithm to a variety of problems, for scheduling problems, structural optimization, network optimization, engineering design optimization. Like that, we have a number of applications. So that's all about this video. If you have any questions, you can comment below. And thanks for watching this video.